Okay, hello and welcome back again to lecture number 18 on this electromechanical systems. Let us do a quick review of what had been covered in the last lecture. We talked about a few numerical problems of PCR design, especially microreactor design in PCR. We saw that if you can really design effectively the time of how a bulk solution of PCR would behave inside a microchip by using this electrical analogy and trying to determine the time constant. We then talked about DNA polymerase, the enzyme which essentially does the replication mechanism inside living cells, and how this enzyme works. So we covered the way the enzyme and the way the fork is kind of replicated in only the 5' to 3' direction, and the formation of short fragments like called Okazaki fragments, especially in the 3' to 5' case. Okay, so then we talked about some electrophoresis basics. Electrophoresis essentially is the movement of charge under external electric field in a medium, and we started to find out mathematically what would be the electrophoretic mobility of the various ions. So we'll start go ahead from there. So as per the few slides mentioned in the last part of the last lecture, we kind of try to equate the electric force that a particular charge, an ion, would face inside a medium to the force that it would face of the frictional or the viscous drag given by the Stokes law, and that led us to the calculation of what the velocity of the ion would be here. It's equal to Zi times epsilon x by 6 pi r times neta. Neta is the viscosity of the medium, r is the radius of the particular ion of interest, E is the electronic charge, that is 1.6 10 to the power of minus 19 coulomb, x is the external electric field, and Zi essentially is the valency on the ion of interest which is moving, which is demonstrating the electrophoretic mobility. So we also discussed that such an ion would definitely experience electrophoretic as well as relaxation effects. The relaxation effects principally come due to the factor that an ion of interest would try to develop its own counter ion cloud around itself, and therefore there is some kind of shielding in the maximum amount of charge that ion has, and also the overall increase in the diameter of the ion. So there is a work center which is let us say a particular ion, maybe a positive ion, and then there is a counter ionic cloud of all the negative ions around it, and this essentially is the ball which is moving towards one of the electrodes, and the counter ion essentially reduces the overall charge by giving some kind of relaxation to the particular ion which is being transported. Let us go ahead and start to derive the electrophoretic mobility from this equation. So there are several factors here. One is that the diffuse layer thickness is really a function of concentration of ions in the solution, and it will go up as the concentration of the counter ion cloud goes up as well. Okay, so let's write some of these factors which are important to mention here. That if you talk about the diffuse layer thickness, is a function of the concentration of the ions, okay, in the solution. And this will go up as this concentration is more. Another interesting thing is that as the field is applied, the particle of interest starts to migrate towards the oppositely charged electrode and drags with it a layer of liquid which is of thickness d, suppose, of the counter ions along with it. Okay, so d is usually lower than the thickness of the diffuse double layer, but it's certainly a finite thickness of a kind of ion shell made up of counter ions which drags along with the primary particle of interest in the solution. So therefore, as the external field is applied, the primary ion starts migrating towards the opposite electrode and drags along a layer of thickness d. Okay, this d is usually lower than the thickness of the double layer which the ion has, okay, the diffuse double layer. So, therefore, due to all these effects there is a kind of shielding on the overall charge of the primary particle of interest. So, let us say that the effective charge of the particle of interest here, which is actually experiencing the electrophoretic force due to shielding by the liquid layer, let us say the counter ionic layer is delta Z, suppose, okay, and now we have a case where this ball of charge has a diameter an initial diameter of radius r, but as the counter ionic cloud comes on this increases from r to r plus d. Okay, d is the small thickness of the counter ion cloud which is much lower than the diffuse layer that the particle would have of its counter ion in the solution, and delta Z being the charge, the effective charge, the shielded charge of the particle of primary interest. The V in this case, the electrophoretic mobility or the velocity V in this case would really be represented as delta Z times of x divided by 6 pi eta r plus d. Delta Z effectively is a unit of charge here, so we do not have to really consider the epsilon value. It is the difference in the charge due to shielding effect, and it is an absolute quantity. The units are in coulombs. Okay, so the capacitance, let us also look at that how this this layer of counter ion and a center primary ion would behave. It would be essentially behaving like the capacitor of a spherical condenser, okay, and which has two plates, one on the inside is a smaller sphere and one on the outside is a spherical shell, and they are separated by a certain distance. Okay, so this is how a spherical capacitor is designed. So this ion counter ion interaction would be identical to the spherical capacitor. Here, of course, because the ions are again in a dielectric which is the water, the solutions are normally aqueous in nature. The counter ionic cloud would have a spacing of several nanometers from the primary charge of interest of a small monolayer of water, the dielectric. Okay, so this again a spherical capacitor model where you have a charge plate analog in this case, which is the particle of interest at the center, another charge plate of the opposite charge, which is the counter ionic cloud in our case, at enclosing this smaller plate, and then the separation distance is covered by the dielectric, which is water in this case. So there are independently these many work centers as small spherical capacitors inside the whole solution. Let us just consider one of them and try to find out what the relationship between the voltage, charge and the capacitance would be in that case. Okay, So let us first calculate what is the capacitance of a spherical condenser. So let us suppose we have this case here where we have a central sphere and then there is a concentric sphere around this central sphere of the opposite charge, and let us also assume that we have two different radii here, A and B. B is the radii of the outer sphere on the inside, and A is the radii of the inner or the core sphere. So electric field in this case, or as a matter of fact in any case, would be given by q by 4 pi epsilon naught square of r, right. That is how the electric field is represented. So the potential between the spheres in this particular case so that means the hollow sphere and the central sphere is essentially the integral of EdR, right. Electric field is the gradient of the voltage or the EMF, okay. So the EMF essentially is the integral of the electric field over this radius r. So it is essentially a radial symmetry, it is a spherical situation. So therefore the only variable here is the radius r. We do not assume any variations with angles, as this kind of from principle of symmetry uniform all through in this particular case. So here the radius is varying between A and B, which is the outer of the inner sphere and the inside of the outer sphere, and if we put the value of E here and kind of try to calculate what this integral would look like, it would typically be coming out as q upon 4 pi epsilon naught 1 by A minus 1 by B. So that is how we calculate the capacitance of a spherical conductor, okay. Now let us go a little bit ahead and see what the capacitance would be. So this here right here is essentially the electric field or the potential V of such a capacitor. If we assume that this spherical capacitor stores a charge equal to q, so C is essentially q by potential, it's equal to q by q upon 4 pi epsilon naught 1 by A minus 1 by B, which is also equal to 4 pi epsilon naught divided by 1 by A minus 1 by B, okay. In our case in particularly in our case, if you assume that the overall diameter has been increased by a term d on the basic iron radius r, so A in our case converges to r plus d, and the B in our case is essentially the capacitance of that combination of ions with the charge delta z with respect to the charges distributed around it all the way up to infinity. So B essentially is infinity in our case, okay. So if we assume that in our model we have formulated in terms of the counter ionic charge and the primary charge of interest. A tends to R plus D, okay, and B tends to infinity. So here is our principal ion of interest positive with a negative counter ion around it. The overall charge is delta Z in this case. and you can assume this charge ball to have a radius initially equal to r, but then with the addition of the counter ion equal to r plus d. Okay, and we are considering this with respect to its whole ambient, which extends all the way up to infinity. Okay, so the B essentially is infinity in our case. So if we put all these two values here in this equation, we get the C, or the capacitance, is essentially 4 pi epsilon naught times of r plus d. Okay, the value for A, and we assume that there is a dielectric constant of d for the medium in which these ions are located. In this case, if you look at the model here, this dielectric constant d was considered to be 1 because this is air. Okay, but because we are talking about ions here, the dielectric constant would essentially be that of water, which is not unity. So there is some value d based on what medium we are using, and therefore in our model the capacitance C can be written down as 4 pi epsilon naught d times of r plus d. Okay, where d is the dielectric constant of the medium. All right. So one interesting factor here that I would like to mention is that, you know, most of these equations have been formulated using CGS units, centimeter gram second units, and this I think I have discussed before in electroosmosis as well, that in CGS units this 1 by 4 pi epsilon naught, essentially this particular quantity, tends to 1. That is how you define the permittivity of free space. Okay, it is a quantity where this 1 by 4 pi times of epsilon naught, the permittivity of free space, is actually 1. And essentially here, if you consider the same CGS units, the C capacitance becomes equal to dielectric constant times of r plus d. By the by, in CGS units, if you look at the unit of charge, that is different, quite different than our coulomb. It's called stat coulomb. Okay, and this accounts for this factor of 1 by 4 pi epsilon naught. So one dyne force between two charges, dyne is a unit of force in CGS as we may recall, is essentially equal to the force between two stat coulombs of charges separated by a distance of 1 centimeter in vacuum, or so that is how Coulomb for the first time defined the Coulomb's law, the inverse square law of forces between different charges. Okay, and here he assumed the stat coulomb as a unit in a manner that he did not have to assume any epsilon 1 by 4, he did not have to assume any value for the 1 by 4 pi epsilon naught, or that was unity. That is how stat coulomb is defined. So when you convert it back into SI units, conversion of coulomb to stat coulomb brings in this factor, and therefore the force in an SI unit can be altered in terms of newtons, and it can be represented by the Coulomb's law as 1 by 4 pi epsilon naught q square by r square. Okay, and this 1 by 4 pi epsilon naught is essentially a factor because of the conversion of stat coulomb into coulomb. That is how you define the charges. So here in this equation, the 4 pi epsilon naught is 0 because we are considering everything in CGS, centimeter gram second unit. So the unit of charge would be stat coulomb there. So C becomes d times of r plus d, and we assume the potential due to the double layer as zeta as the capacitance due to the double layer. Okay, so the capacitance being d times of r plus d is the capacitance of this primary ion surrounded by a counter ionic cloud, and if we assume the surface potential of this particular ion of interest to be zeta, then the capacitance C is essentially the total charge of the ion and the counter ion due to the shielding per unit the voltage, which is the zeta potential, and it can be equated to d times of r plus d. Okay, and so the delta z in this case is nothing but d zeta times of r plus d. So that's how you define the additional charge of a particle that takes up by formation of this counter ionic cloud in a particular solution. Okay, if we go back to our equation on the electrophoretic mobility, and try to derive a formulation or a relationship between all this delta z value that we obtained here and our equation. So V there was essentially represented as delta z times of the electric field x divided by 6 pi neta times r plus d, when neta was the viscosity of the medium in which the electrophoresis is happening and x is the external electric field. R plus d remains the same radius of the modified ion with a counter ion cloud around it. Okay, so if you put this value of delta z here in this equation, you obtain a V value equal to d times of zeta x by 6 pi n. So that is the only difference that the mobility or the velocity, electrophoretic velocity in this case has over the electrosmotic case, where this was d zeta x by 4 pi n. So the 6 pi is the only difference that this mobility has, okay, the ion mobility in the electrophoresis has over the electrosmosis. And essentially the mobility is also defined as the velocity per unit electric field. So if x is 1, then the mobility in this case would be d zeta by 6 pi neta. D is the dielectric constant, again zeta is the zeta potential of the ion counter ion combination, and neta is the viscosity of the medium. Okay, so all said and done, this is what the electrophoretic velocity or mobility would be defined as. We just go into the practical aspects associated with this electrophoretic process. So essentially electrophoresis is very widely used for fractionating DNA molecules, as I have already suggested before, especially using sieving matrices with a series of nano level channels, or at least channels which are 100 nanometers or more in diameter across the matrix, and these are essentially gel materials. Okay, so they have a solid phase and then they have also a participating liquid phase in it. So as the DNA is loaded and pushed through these sieves, they have a tendency of differential frictional forces directly proportional to their length, and therefore longer the molecule is, slower it would move, and there would be a fractionation and the molecule will kind of go and split up after a while into shorter and longer fragments. Okay, so the important aspects about DNA gel electrophoresis are the following, that essentially DNA has a phosphate backbone which is negatively charged, hence it drifts in an E field. Okay, the charge to mass ratio of a DNA is constant, and therefore electrophoretic mobility is independent of size in a liquid medium. If you put this DNA or any other thing in a liquid medium, just because the charge to mass is nothing but constant, if the size increases, the charge and mass both increase proportionally, so that E by m always remains same, and there is no difference on account of E by m. However, so therefore if you put it in a liquid medium where there is no sieving effect or there is no frictional effect, it will move as one blob altogether, whereas in case you put it in a medium which is like a gel material, there would be some differential mobilities independent, or which is dependent on the size, just on account of the friction that the medium would provide to the DNA molecules. So therefore another sieving medium is needed where separation can take place due to difference in lengths, and the separation region is filled with a gel sieving matrix with pores through which DNA molecules can traverse, and the field stretches the molecules and they move like in a snake like manner through pores of the gel, and the electrophoretic mobility mu in gels is inversely proportional also to the log of the fragment size, or this is essentially known as the sieving effect. Okay, so the mobility would be more if the logarithm of the fragment size is essentially more, or vice versa. So also there are several such gel materials which are used from time to time. There are various kind of gels which are used for this electrophoresis. Agarose is a very common gel material that is very often used, and I'll just in about 1 or 2 slides try to discuss some of the molecular structural aspects of the agarose molecule. And another very important interesting high resolution gel material is polyacrylamide And there are several other sieving media which are used time to time for electrophoresis, one of them being F127 or pluronic. It is a molecule which has a combination of polyethylene oxide and polypropylene oxide in a manner that it forms micellar structures, and when they come very close together and there is a certain density of these micelles inside the solution, they also make cubical lattice kind of arrangements, and also result in these finely distributed channels. In that case the channel sizes is much smaller, about 10 nanometers or 20 nanometers, and therefore that gel is more clear because it essentially holds less amount of water. Okay, so there is less scattering of light. Agarose on the other hand is a very milky, very turbid medium because of the presence of a large amount of water. Mind you, in media like agarose, the pore size distribution is roughly about 100 nanometers plus minus a few tens of nanometers. Okay, it's about 10 times that of F127 or other smaller pore media, and that also is one of the reasons why the light gets heavily scattered in a media like agarose. The way you make these gels are that you actually have agarose as powder or all these other materials as powder which you dissolve in either an ionic buffer or an aqueous medium and then melt the molecule, and that can be done by heating the medium using a microwave or some other mechanism for a long amount of time, so that it kind of tries to melt the molecule and make a viscous slurry out of this mixture. And once this is allowed to settle and cool, there is this development of several nucleation centers, and there is a slow development of the gel phase which contains a lot of water as well as the solid media. So solid material. So polyacrylamide gels is used to separate DNA molecules of 10 to 500 bases. Pores are small, resolution is high. And agarose on the other hand are used to separate larger molecules, about 300 to 10,000 base pairs. Pores are relatively large in this case, although the gel material is very milky and it is really not a very good sensing material as far as electrophoresis happens in thin capillaries, etc. An interesting factor here that I would like to discuss is some of the recent trends of research that has happened starting from Benjamin Chu's group in this electrophoresis area, where they have tried to address one of the major problems in electrophoresis of DNA, that as the DNA size goes above a few tens of kilobase pairs, there is a tendency of the gel to lose its resolution or its ability to fractionate or separate different DNA strands. Okay, one of the reasons why that is so is that if you look at the way that the DNA moves through the gel, it is like a serpent. The pores are all randomly distributed in the whole gel matrix, and as the DNA is moving around, there is a head of the serpent which goes into one of the pores, and it tries to realize, or it just realizes that it's not having enough order in the section that it is entering for the whole tail to go through, and therefore it is stuck up there. It cannot go any more further, even though you have increased the field or you have done some manipulation with the drive force that the DNA has. Okay, so in this situation what happens is that the DNA kind of stays there and kind of jumbles up, and there is a loss in resolution. So this is also known as biased reptation, and it happens in if the DNA sizes are excessively large, let's say 10 kilobase pairs or longer, and therefore in such situations a very good idea is to rather go from a three-dimensional bulk into a surface, and this area is known as surface electrophoresis. So you have a situation where you have some DNA molecules which you physisorb on a certain surface, let's say a silicon dioxide surface, and what happens there is that you have an interacting surface, you have a DNA molecule, and you have some kind of a media, liquid media over that DNA molecule, and so the DNA essentially forms a loop train kind of structure. And the way these are formulated is that there are portions which are adsorbed on the surface of the DNA, and there are negative loops which are extending into the solution, something of this order. So you have, let's say, a surface here, and you have a DNA which is physisorbed on the top of this particular surface. So it actually has this loop train kind of jumbled up structure. So you have these portions here which are adsorbed physically on the surface, and these portions which are projecting into the solution which is over this surface here, and these are like loops. So one important aspect here in surface electrophoresis is that longer the DNA molecule is, lesser are the number of loops. Okay, the loop lengths kind of reduce, and more are the number of these trains of the adsorbed portions on the particular surface, and therefore the longer molecules are kind of held firmly to the surface as opposed to the shorter molecules, and that gives you a reason of fractionation. And in this case, when you are trying to drive the molecules by putting an E field on the medium over that surface, the loops kind of try to dance around, and there is a gradual shifting of the molecules towards the positive electrode, but in the process the longer ones being more firmly adhered fall back and move slowly. Okay, the longer ones and the shorter ones which are having more loop structures and lesser train or lesser absorbed areas on the surface would move faster, and it gives a basis for fractionation. So I would be in one of the future lectures probably trying to show you some of the experimental results that even our group has developed in this area of DNA electrophoresis on a surface called surface electrophoresis. So let us look at some of the basics of these novel gel materials. Agarose is a very famous molecule which is obtained from essentially seaweed. Okay, it's an extract which has been chemically derived from seaweeds. Agarose in a chemical classification falls in the domain of polysaccharides. Saccharon again is something which came from Greece. It's a Greek word meaning sugar, and monosaccharides, and there are many kind of such sacharons. Saccharon can be as a monosaccharide, where it is a simple sugar consisting of a single polyhydroxy aldehyde or ketone, something like this. Okay, it's called let's say this glyceraldehyde is a kind of sugar, or this alpha D glucose is a kind of cyclic form of hexose. It's again another sugar, but essentially it is only one member, one single polyhydroxy aldehyde or a polyhydroxy ketone. That is what monosaccharide is. Okay, one sugar molecule, one saccharon. A disaccharide is a combination of short chains of two or more monosaccharide units with a so called glycosidic linkage. Okay, so a glycosidic linkage is something like this. It is a CHO and another C here and H on another side, and so it's essentially COH2. Okay, that's what a glycosidic linkage would be. So a disaccharide essentially is an assembly of two monosaccharide units with a glycosidic linkage in between, as illustrated or as shown here. So this by the by is maltose, which is a disaccharide. Okay, agarose however is a polysaccharide, and it's actually a combination of 20 or more monosaccharide units, or 20 and more sugar molecules. The D-galactose here, if you see, and this flank here is D-galactose, this flank here is anhydro L-galactose, and there is a glycosidic linkage in between all these different sugar moieties or sugar groups. Okay, so agarose is a combination of more than one and more than two, in fact, sugar molecules. So let's see what happens or how it behaves when you put agarose in a solution. Let's say a aqueous solution with some kind of a polarization aspect. So here is a case where this two units of sugar, which is joined also in a chain like fashion in the agarose, has been illustrated. Okay, and this when put in water has this tendency of the various OH moieties, okay, hydroxyl moieties, to interact with the HO H2O. Or water to form hydrogen bonds. Okay. So, by virtue of having so many hydroxyl groups in these different sugar molecules, they almost always tend to form hydrogen bonds with the surrounding water or among themselves, okay, among itself. And therefore, there is this tendency of this particular molecule to turn around its axis. Okay. So, one half of the molecule would take a clockwise rotation, if you see from this end, and the other half would go in the anti-clockwise direction around this central glycosidic linkage of the central bond, as here, right. So, it is illustrated here. So, this part of the molecule moves in the anti-clockwise direction, and this is in the clockwise direction if you see it from this end. Okay. You visualize it from this end, and therefore, because of this rotation of the molecules which is happening, and several such centers are developed, we develop coils, molecular coils, and these coils are essentially what comprise the pores of the gel materials. So, you can see here in this figure. So, there is a solution in which you have put these agarose molecules, and they have started forming these coils kind of framework in the presence of water, especially when they get molten, and then they can get some organization, and or they can actually start nucleating in various centers, and that is how they can get a randomized porous nature all through the surface. So, summarily, due to the development of hydrogen bonds in water solution, there is a confirmed combination of these two angles, the phi and psi. Here the angle of movement on the left flank is termed as phi, and that on the right flank is termed as psi, and these are defined by eventually what is the energy state, thermodynamic state of the molecule that it is in, okay, or the amount of hydrogen bonds between themselves or between the media that they formulate. So, due to development of hydrogen bonds in water solution, there is a confirmed phi psi combination for the least energy configuration, and for all starch molecules including agarose, the best combination giving the most stable structure is a tightly coiled helix. Okay. And there are these helix centers which you can see developing inside the gel material, which can be organized or disorganized, and that is how the agarose forms a set of nanopores within the whole gel material. So, these pores can also be illustrated here. If you look at these pores, this is essentially what the DNA molecule looks like. It is like a jumble of double stranded features, and then when you apply a negative and a positive potential in two ends of this gel, there is this tendency of this molecule to get pushed through as a flat or as a thread, as a snake, and then it moves throughout the gel towards the negative end, and you can see this illustrated here by some of these figures which have been borrowed from a paper which was published some time back also in Nature, which talked about these DNA separation chips and the way DNA would be separated using nanospheres, using gel mediums, or using all sort of combinations. Okay. So, you can see here how this fluorescently labeled DNA is kind of stretching out, and as it goes along it kind of again after a while rests at a area of the gel. Okay. So, that is how you can interpret DNA translation in agarose or electrophoresis in general. Alright. So, with this it kind of brings us to the laboratory aspect of how electrophoresis can be done in a laboratory to fractionate or detect PCR products. So, one aspect of electrophoresis is also how to make visible the DNA stains which are there. So, on a laboratory scale, electrophoresis is used mostly for studying the sizes of PCR segments, PCR amplified segments. The idea is that if you have design primers for a particular DNA sequence to pick up, let us say a particular address, okay, representing or which is a representative of a certain cell type. So the address is actually related to not only the end flanks on the DNA, the first 20 or 30 base pairs on both sides of the DNA, for which the primers are meant for, but also the overall length of the segment that the primers are able to amplify or cleave off from the overall from the otherwise elongated or full sized DNA molecule. Okay, so electrophoresis is essentially an additional detection step for confirming whether we are amplifying the region of the DNA which we are supposed to amplify by using the uniquely designed primer set reverse and forward in the PCR reaction. So one of the ways of comparing this length is also to run it parallel to something called the DNA ladder. A ladder essentially is the same concentration of different fragment lengths starting from, let's say, 100 base pairs all the way to about 1000 base pairs, with a difference of about 100 base pairs. So you have a solution, and these are commercially available in most of the companies which sell PCR based products or kits, and they are also known as DNA ladder technically. Okay, so let's say you have 100 to 1000 base pairs with 100 base pair difference. It essentially would mean that you have 100, 200, 300, 400, 500, so on up to 1000 base pairs DNA fragments of equal concentrations mixed together inside the ladder. So when you run it on a gel and you let electrophoresis happen, after a while you will see that there are stains which are coming up. By the by, the stain comes up because you have a fluorophore molecule which you either load inside the gel, and the idea is as the DNA moves along with the gel, it kind of picks up and intercalates with the molecules that it meets in the way, okay, as it's moving from one electrode to another, and starts glowing. Another alternative is to actually pre-induct these molecules into the cage-like structure, or pre-intercalate these molecules into the cage-like structure, so that automatically there is a glow fluorescence which is being generated. And now if you run this fluorescent dye coupled ladder through the gel, there are this series of bands which come up along the length of the gel, starting from 100 all the way to about 1000 base pairs. So now suppose you are picking up a PCR fragment which is about 524 base pairs. So essentially it should fall between 500 and 600 step on the ladder. That is how this looks like. If you look at some of the gel experiments in the laboratory scale, as you are seeing here, these particular figure here shows these bands, right? These are fluorescent bands. The fluorescence comes out again of the intercalation process between the DNA of a certain size and the fluorophore material which is present in the medium of interest. So you have these different bands starting from 2.5 million, 950,000, about 610,000, 220,000, so on and so forth. These are nucleotide pairs, the number of pairs, okay, that are available. So you can see again the different lengths with different such combinations, and this is very often done in a sequence readout, which we'll be doing in details later. This process is also called the Sanger's process, wherein you can actually record on a one base pair by one base pair difference what is there in a particular DNA molecule, okay. And when you run it through these 4 different gels, you can have an idea of what follows what. So is there an A first, or a G, or a T, whatever is first, and then what is the sequence like. All this information can be had from such a readout, okay. So it's there also you are using gel electrophoresis to find out an information about the sequence, coupled with a characteristic fluorescence for the type of molecule to be A, T, G, or C. We will be talking about this process in one of the later lectures in great detail. It's called Sanger's reaction, and this is one of the fundamental principles of gene sequencing. So the way you do it in a laboratory is that you prepare a gel material with pockets, something like this, and then you essentially put the mixture of DNA fragments of different sizes into these pockets. As you can see here, the DNA is being loaded onto the gel. This principle is also known as loading the DNA, okay, in different points here. And then you have an electrode set with an external power supply which applies a voltage, making this side the anode and this the cathode, so that the DNA gets pushed off and starts translating electrophoretically towards the anode. And you can see these bands start developing after a while as the DNA moves through the gels. Essentially, after a longer amount of time, the longer fragments kind of huddle back, okay, and the shorter come ahead, but they are all separated because of their different frictional forces based on sizes, and that's how a completed gel would look like. The way you actually read these out is pretty simple, because the dyes you are using have a UV based excitation frequency. You put this gel material over something called a transilluminator. So this is nothing but a source of UV light with a few tubes which would contain either a biwavelength or a monowavelength UV ultraviolet light being generated. So the gel is placed on the top of a glass plate which is covering or it's the housing for the particular set of tubes, and then automatically as the UV is switched on, you will see stains getting developed or getting visualized or optically becoming clearer. And the stains are essentially, depending on the dye that you use, have several different emission frequencies. Two most commonly used dyes are cyber green and ethidium bromide, ETBR. Okay, so ETBR has a frequency in the range of about 620 nanometers plus minus 10 nanometers, and essentially this is something which appears to be pink in color. So the fluorescence developed is pink fluorescence, and cyber green on the other hand is more towards the green wavelength. So this is a guy here shown who actually is trying to read out what is there on a gel by looking at the sample placed over this transilluminator. This is what the transilluminator would look like, and you have to be careful while reading out a gel in a laboratory of protecting your face, because UV essentially is also damaging to the epithelial layer of the body and can cause skin cancer. So you may have to be careful about your wares or your safety mechanisms properly before looking through such a gel illuminator, transilluminator. There are nowadays to prevent the UV exposure, there are automated devices called gel dock systems, wherein there is a camera which would be able to record what is there on the gel. As the transilluminator is switched on, there is a hood which covers the whole transilluminator, and the top of the hood there is a camera, and you can pick it up on a camera and actually visualize it on a computer screen by looking at the corresponding CCD image, okay, or the camera image of the particular gel material. So that's what electrophoresis is. This is actually done in a bulk sample, okay, and it essentially lacks speed, again because of the fact that you are able to only generate voltage or apply a voltage good enough for ensuring that there is not substantial heating, so that the gel can remain in one integral form without any melting in between, okay, and therefore the voltages that you can really go up to are really just a few hundred volts, and that terribly makes the electrophoresis process slow, and the DNA would take its own time, own sweet time, probably a couple of hours to migrate through these gels and finally lit up, and therefore the process is a low throughput one because of this reason. Now we have been talking this off and on, that because the Human Genome Project necessitated great rapidity or tools which could be more sensitive and rapid, and at much more minuscule samples could be successfully interpreted. Therefore people started thinking about what would happen if you could really introduce this more surface area to volume ratio concept in case of electrophoresis as well. Some of the most prominent amount of work, most prominent research work which was developed with this concept in mind is also what is known as capillary electrophoresis. Okay, so essentially in this capillary electrophoresis, so capillary electrophoresis definitely has been explored very often, where this gel material is actually injected and coated inside a very thin microcapillary which may be several microns thin, and although the resistance in that case increases hugely, but then the fact is that because of a higher surface area to volume ratio, there is a greater heat transfer, and the melting of the gel material or the medium separation matrix doesn't place that often, and or it takes a higher amount of voltage for causing enough heat to for the gel to melt. And so the operation range of the electrophoresis process increases hugely because of that, and fields or voltages, external voltages as high as about 1000 to 2000 volts can sometimes be utilized very well for causing the DNA to migrate, and therefore in capillaries they migrate much more faster, and this process becomes extremely rapid because of that. So in a conventional system, as you know in laboratory you have typically a PCR machine, so initially you have DNA extraction machine where cells are lysed and the DNA is subsequently captured on filters. You have a PCR machine illustrated here. This is like what a normal thermocycler would look like. There is a huge aluminum block here which although can be used for doing more than one samples and make the process high throughput, but then the fact is that the overall time here is much higher. It is in the range of some hours, and microsizing the PCR essentially would prevent this consumption of huge consumption of time in a normal size PCR thermocycler. Such cyclers are actually of the form of a desktop computer if you consider the size aspects. This is a sample preparation hood where a PCR mix and other DNA related sample preparation can be executed. This essentially is how an electrophoresis tool would look like. This is an electrophoresis bench which is used for gel electrophoresis, and this is a transilluminator and a hood that I have been talking about in the last slide. This is how the whole laboratory is built up. So you have an extraction of DNA, you have mixture preparation center, you have PCR module, and the post PCR products you pass through a gel and then read it out on this transilluminator and the gel reading system. So there have been initiatives to kind of compress all this of the size of a whole room size laboratory onto a single chip, and in fact there are ideas and papers which have been developed by researchers around the world where they have seen how miniaturization of this whole lab on a small chip can help in extremely rapid analysis of DNA that can be done otherwise on this kind of a scale, and make it much more portable, much more friendly, much more amenable, and also much less expensive process, okay, because of the reduced use of reagents, etc., and also reduced amount of energy that is needed for doing the rapid thermal cycling. So this in a nutshell is also known as integrated gene analysis system. So capillary, on the other hand, capillary electrophoresis is something which also can be miniaturized very well into small microchip platforms. In a nutshell, some facts and figures about DNA electrophoresis is illustrated in this particular slide here. You see the separation distance delta L between two different fragments with various mobilities, okay, as you are moving through a gel matrix. So this is the distance between two stains of different lengths. So there it's proportional to the differential mobility of the two segments, two different lengths, proportional to the field which is applied and also the time for which the field has been applied. So delta L essentially is between these two bands, okay. The distance that two bands move with respect to each other, the minimum distance of separation that two bands have at a point of time t, and which is also in an electric field E, and let's assume that there is a difference in mobility of these 1 and 2 stains which are separated by delta L in this case. So resolution of the separation is measured by planes n, where n is the number of distinguishable bands within the length of the gel squared. So if you have a, let's say, 100 to 1000 base pair DNA, and if you get exactly 10 distinguishable bands, or exactly 9 or let's say 8 distinguishable bands, so the resolution essentially is only 64. Okay, that's what it would mean. And the way that resolution of a gel, this is a mathematical quantity, is correlated to the mobility of the molecules, the velocity, the electrophoretic velocity. Also the diffusion coefficient D is illustrated here in the figure. N is equal to mu V by 2D. D is the diffusion coefficient. Of course, some other facts and figures are that higher voltages would increase the resolution, but Joule heating being an issue, you cannot really go on shooting the voltage to a very high level. Okay, so essentially that's what one constraint is, what is offered for by a gel matrix on the control level of the voltage. And separation can also be done in capillaries again, which I have been talking about, since higher fields can be used and higher velocities and shorter times can be achieved. So let us look at some of the modules for capillary electrophoresis. So definitionally again, electrophoresis of nucleic acids within capillaries 75 to 100 microns, using minute sample volumes and achieving a higher stain resolution. Okay, one advantage of such systems is that because of the higher surface area to volume ratio, this kind of enables higher electric fields with minimal Joule heating. Agarose, polyacrylamide, hydroxyalkyl cellulose, polyvinyl alcohol and its copolymers are some sieving matrices that are being used regularly for capillary electrophoresis. The disadvantage of such a process is that it's not very field applicable, particularly because of the higher voltages in the range of 1 to 3 kV are very often used for doing this capillary electrophoresis. So what this really means is that you can take it onto a small capillary. This right here is an illustration of how you can presume what capillary electrophoresis can do. So this is a mask of a capillary system. Here if you see, there is a set of crisscrossing channels. This is the feeder channel. Okay, so you can also use it for sample loading, and this is the main channel here which does the electrophoresis. By the way, these all channels are in the range of about 100 micron thickness. Okay, this starts right here at about 1.5 mm and goes all the way to about 0.5 mm here. Alright, and these are reservoirs. These small circular moieties here or features here are reservoirs. So you can feed the DNA here and electrokinetically inject it into the gel in this region, and then you apply a positive and a negative, and the DNA would start flowing in this direction. Okay, simultaneously if you change the voltage, the DNA would start moving in the opposite direction, and you can have these bands of fractionation developed within these particular areas as the DNA goes and moves. Okay, so here this process is illustrated here in a little bit different manner. So using pressure driven flow, you can introduce this green sample, which is the DNA labeled with dye, onto the small thin capillary here, and here you can also simultaneously introduce gel material by a two directional control. And the idea is that you leave the gel open for just about a couple of milliseconds. The gel kind of evaporates, the gel kind of solidifies and hardens and fills the whole capillary. So you now have a plug here of the particular DNA molecule which you can move with electrophoresis. So this kind of brings us to the end of this lecture, and we will start with this new capillary electrophoresis topic a little bit more and try to finish this in the next lecture. Thank you.